another important topic in physics is the variable movement. So imagine that you have an object, a vehicle, moving with steady velocity and steady acceleration. X naught, you can see X naught is the initial position where my vehicle starts. Y naught is the initial velocity of my vehicle. V and A is the velocity and the acceleration. X is the distance traveled, the distance that the moving object has traveled. What we can do is we can derive these equations using techniques from analysis. So we know that the velocity is the derivative of x with respect to time. What we can do is write the differential dx equals v times the differential dt. I integrate from x naught to x. And here I integrate from 0 to t, from 0 to t. Let's take that my movement is with a constant velocity, so I can take it outside the integral. So the first integral here is x from x naught. So with this, so I have to evaluate this. And this is v times t from 0 to t. This is x minus x naught equals v times t. X equals x naught plus v times t. So for t equal to 0, x naught is this value. So x I evaluated at 0 for time equals 0 is x naught. So this is xt equals x naught plus v of t. This is a straight line. I can get the position if I know the time t, and if I know the initial position. Usually we start from x naught equal to 0, and v is the slope of my line. Let's go and derive the next one. We can derive the next equation. V equals v0 plus a times t. So we know that the velocity, the acceleration, is the derivative of the velocity with respect to time. So the differential dv equals a times dt. I integrate from an initial velocity v0, and here I integrate from 0 to t a dt. I take into account that a is doesn't depend on, is a constant acceleration. So I can write it like this: integral from 0 to t dt. This should be v minus v0 equals a times t. V equals v0 plus a times t. For t equals 0, v0 equals v with index 0. So this can be written as v of t equals v0 plus a times t. This is the velocity is a function of t. So this is a straight line. V0 is the vertical, the intercept in the vertical axis. A is my acceleration, as t is time. So the slope of this line, the gradient of this line is a, is appearing in front of t. How can we derive the last one? So x equals x naught plus v0 times t plus a half a t squared. So we take this relationship here, v equals v0 plus a times t. So v is the derivative of x with respect to time, v0 plus a times t. So the differential dx equals v0 plus a times t dt. So this can be written as v0 dt plus a times t dt. I integrate, x0 is my initial position, and this I integrate from t equal to 0 . So this is x minus x0, the left-hand side. This is v of 0 times t plus a t squared divided by 2. So from here I have x equals x0 plus v0 times t plus a half a t squared. So here my position depends on the initial position x0, the initial velocity, and also acceleration appears here. So let's go back and do a small recapitulation. We can derive the first equation for the position by taking that the velocity is by definition the derivative of x with respect to time. I integrate, I assume that the velocity does not depend on time, it's constant. So I can pull it out of the integral. So after doing some trivial calculations, I have that the position is a function, a straight linear function, where x0 is my initial position. The slope, the gradient of my line is the velocity, and of course t is the time. For the second equation, I take the definition of acceleration, which is the rate of change of the velocity with respect to time. I solve with regards to the differential of the velocity. I integrate from v0 to v, and I consider that the acceleration is constant, so I can remove it out of the integral, and I obtain that the v is a function of time, and here v0 is the initial velocity, a is the gradient of the line, is an acceleration, and t is time. For the last equation, what I have to do is take that v equals the sum of the initial velocity plus the product of the acceleration with the time. The velocity is the derivative of the position with respect to time. I solve with respect to the differential of x. I integrate both sides. Okay, and then what I have is I can compute the integral at the left-hand side and the two integrals at the right-hand side. So what I can do is solve with respect to x and have a function, a relationship for the position given the initial position, the initial velocity, and the acceleration, and of course time.